Hello, myself Naveen Kumar Sani. In the course Electromagnetic Field Theory, today we are going to discuss about the magnetic forces. In that series, this is lecture number 16, we will discuss about the boundary conditions and the magnetic energy. So, as we have discussed in the electrostatic as well about the boundary conditions, in that we have taken care about the three cases. So, first case was the I hope you remember that in the electrostatics. Okay, so first case which we have discussed about the dielectric case. So this was the dielectric case. Second case which we have discussed about the dielectric and the conductor, and third case which we have discussed about the dielectric, or you can say free space. So this was the free space and the conductor. So we have discussed these three cases in the boundary condition of electrostatic field. Okay, so now we will discuss about in the magnetostatic field, that is magnetic boundary conditions. So same as we have used the two Maxwell's equations or the two laws in the electrostatics. Okay, Gauss law, and there is another Ampere's, that was the E del cross of E is equal to 0. So these two cases we have covered, right, in the electrostatic. So del dot D is equal to rho v and the del cross E is equal to 0. So these two Maxwell's equation we have used in the electrostatic. Now we will discuss in magnetostatic the two laws we will apply, use Gauss law and the Ampere-Circuital law. So which was given by the Gauss and Amperian. So here the first is your Gauss law, that is B dot ds is equal to 0. Okay, we have discussed about that. So this was the no monopole exists for a given volume, okay, in the magnetostatic field, that is B dot ds is equal to 0. So important point is here, that is the closed surface. Okay, so from here we have derived the Maxwell's equation, that is B del dot B is equal to 0. So we have derived by using the divergence theorem for that. Second one is the Ampere-Circuital law. So for this Ampere-Circuital law, which we have del H dot dl with a closed path, that is equal to I enclose. Okay, so from here we have derived another Maxwell's equation. So this Maxwell's equation was del cross H is equal to J. So we applied the Stokes theorem in this equation. So we derived the del cross H is equal to J. So these two equations, del dot B and del cross of H, these are the differential equations, and this B dot ds and H dot dl, these all are the integral form of the Maxwell's equation. So we are going to use these two equations for finding the boundary conditions in magnetostatic field. Okay, so as we have already covered about the what is the boundary conditions in the electrostatic, where we said one medium is there, second medium is this, then intersection of or the interfacing between the first and second medium, we have to find the boundary condition for that. So same procedure we have to use in the case of the magnetostatic. So here we are using the general case where the mu1 is the medium 1, mu2 this is the medium 2, right? So medium 1 is defined by the permeability mu1 and medium 2 is defined by the permeability mu2. Okay, so in this we are just discussing about the magnetic field. So here in the medium 2 the magnetic field is B2, and corresponding to that in the medium 1 we are assuming the magnetic field is B1. So this is a magnetic field density, flux density. So B1 and B2, these are medium 2. Okay, so the what is the significance of that? If we know the value of B2 or we know the value of B1, then respectively we can find the B2 and B1. Okay, So if B2 is given, then B1 we can find out. If B1 is given, then B2 we can find out by using the boundary conditions. So then what we have done, we will use these equations. So before that, what is the important point is, we divide this B1 in the two components. B1 is equal to B1n plus B1t. So this is the B1 in the medium 1. We are dividing it into two parts, B1n plus B1t. Second is the B2. B2 is B2n plus B2t. Okay. So in the medium 2, B2 is B2t plus B2n. So these are the two components. Okay. So this is nothing but the B2n. So these are two components for the B2, that is B2t and B2n. So these are two components. Okay, so we will apply the first of the Maxwell's equation, that is del dot b ds. B dot ds is equal to 0. So this is a closed surface. So in this case, we can see we will take one of the path or one of the surfaces which enclose this boundary interfacing between the two medium. So B dot ds is there. So B1 and B is nothing but this is in the medium 1, this is B1n plus B1t. In the medium 2, this is B2n plus B2t. Okay, so here we can see we are taking one of the surface. So in that direction of surface is this one, and here this direction is this one. So in the as we are talking about at the boundary condition, so what we have to take? We have to take care about the delta H tends to 0. So all the cases are there where we have the delta H tends to 0, which is the height of this pillbox. So how we can find it? So this is nothing but B is in this direction. So this is nothing B1n. So this is B1n. This is in this direction, and delta S, yeah, ds is in this direction. So we are defining this delta as the ds is that is we are defining delta S. Okay. So both are in the same direction, B1 and delta S. So if it is the in the same direction, so we can write that is B1n into delta S. This is in the medium 1. Now come to in the medium 2. So in medium 2, we know that the direction of B2n is in this direction. Okay, B2n is in this direction, and B2t is in this direction. So but we are interested about the delta S. So in this delta S is in downwards, right? Suppose this direction is the z direction. Okay, so if the normal component of this one is in z direction, so here this will be opposite of minus of az direction. Okay, so delta S is in downwards and the B is in upwards. So delta S, we can say this is the downward case, and B2n corresponding to that is the upward. So delta S is minus az and B2n is az direction. So it means this is opposite in direction. So it means this will become the B2n into delta S with the minus sign. So here B2n delta S with the minus sign. So B1n delta S minus B2n delta S, that is equivalent to 0. So I hope this point is clear to all of you. We are using this pillbox. So here the direction of delta S and B1n is nothing but that is equal to that is in the same direction. So we are simply multiplying this one, and the below of this pillbox, this is in the downward direction. So delta is in downward direction and B2n is in the upward direction. So opposing direction, because of that this will be with the minus sign B2n in delta S. Okay, so we are defining like this. So B1n delta S minus B2n delta S is equal to 0. So delta S cannot be 0, but delta H, we are taking delta H tends to 0. It means we are talking about the interface. So at the interface means delta H must be 0. So the condition will become B1n is equal to B2n. Okay, so this is one of the boundary condition, that is B1n is equal to B2n, which is continuous. So in words we can say that the normal component of magnetic flux density is continuous at interface. Okay, at interface means delta H tends to 0. So normal component of magnetic flux density is continuous at interface. At interface means delta H tends to 0. So this is the case for the normal component. Okay, so in this way we can also define, we can convert as B is equal to mu H, right? So in this case we are defining it like this. So B1n will be mu1 into H1n is equal to mu2 into delta H, H2n. So it must be visible to all of you. So I am simply defining it like this. Okay, fine, good. So now we can see that mu1 into H1n is equal to mu2 into H2n. So that is equivalent to, so in this way we can say that the normal component of magnetic field intensity is discontinuous at interface. Okay, at interface means delta H tends to 0. Okay, so the normal component of magnetic field intensity is discontinuous at the interface. Normal component of magnetic flux density is continuous at the interface. Okay, so this is discontinuous because of this factor mu1, and this mu1 and mu2 is involved into it. So the H1n and H2n value will be defined or differ because of the mu values, right? Okay, so now come to the second case where we have the magnetic field intensity we are using here. So for that one we have to find, we have to use one of the Maxwell's equation, so which is defined as the by the Ampere circuital law, that is H dot dl is equal to I enclose. So H dot dl is equal to I enclose. So here I is equal to I, so we can define the I is equal to K into delta V, so delta W. So as we are aware about the K is nothing but this is the surface, this is surface current. So this is the surface current. So this surface current, what is unit for that? Ampere per meter. So if the unit for that is ampere per meter, so current will be what? Current I. So we can define the current, that is equal to K into width of the current sheet, right? So if you are when we are discussing about the Ampere circuital application, so second application was the infinite sheet current. So there we have assumed that when we are looking from this side, from back side of the current carrying conductors, so we see the crosses are there, right? And in that way also we have defined that the direction of H was in this direction when it is the Z greater than 0. When it is Z less than 0, so in that case the direction of H was in this direction. Okay, so this was the cases which we have discussed in the previous cases, but now we are very much interested about to apply the H dot dl. So okay, so what is the delta W? So in this case we see delta W is nothing but this is the width of the current carrying conductors. So if we have the 10 current carrying conductors are lying, so the total width which is carrying the all the 10 current carrying conductors, these are delta W. Okay, so now we can apply here, that is H1t. So just move into this direction because we have the DL. So for the path we have to take, that is A to B, B to C, C to D, and D to A. Okay, so we have to move in this direction, A to B, B to C, C to D, D to A. So for come here for A to B, right? So for A to B, the direction of A to B and H1T is the same. So we can write as the H1T into delta W because the directions are same. H1T from here and delta W from here. So we have to multiply these two components, H1T into delta W. Now come from B to C. So one segment is over. So second segment is divided into two parts. First segment is in the Z greater than 0 and second segment is in the Z less than 0. So here we see that in this direction, so in the medium 1, sir, so this one is the medium 1, this is medium 2. So for the medium 1 we have H1N, right? So in the medium 1 H1N is in the above direction. If I am saying this is AZ direction, so H1N is in the positive Z direction, and when we are moving from B to half of this, you can see B dash, so up to here. So this direction is downwards, so delta H by 2, so this is downwards. So in this case what we have to find, we have to see H1N must be with the half of delta H by 2 with a negative sign. So here I think wrongly mentioned here, so this will be minus of H1N delta H by 2. So now come to the second part of this one. This is in the direction, in the below direction. So this is in below direction, H2N is upper direction. So H2N is in the upper direction. So in this case we see H2N and this one is half. So we have to use again the with the minus sign. So H2N delta H by 2. Now come from C to D. So for the C to D, what we see, delta W is in this direction and H2T is in the opposite. Okay, so these are opposite direction. So this value will be H2T into delta W. Both are in opposite direction. So with the negative sign it will be H2T delta W. Now come from D to A. So for the D to A, what we have, this half is in the medium 2 and this half is in the medium 1. So in the medium 2 is the H2N. So H2N is, this is the parallel with this. So H2N into delta H by 2. So the direction of delta H is in this direction and delta H, H2N is in this direction. So both the directions are same. So it means this value, this is the product which is a positive sign. So H2N into delta H by 2. So H2N into delta H by 2. So this is the with the positive sign because both are in same direction. So here next is this one. When we are moving in this direction, second half of this, so this was the first half, this is second half. In the second half, delta H by 2 is in upper direction and H1N is in the upper direction as well. So this is in upper direction, this is in upper direction. So both are parallel, both are in same direction. So it will be H1N in and 2 delta H by 2 with the positive sign. So this will be positive sign. Okay. So this is a simple thing which I am trying to say. So this is maybe the rearrangement of the equations, but terms into the equation. But what I wanted to explain you in that way, so that in the sequence things must be clear to all of you. Okay, so I have just used this in the sequence manner only, so that the you must get the complete intuition about this equation. So H1T delta H by 2 minus H1N into delta H by 2 and H2N this one and H2T delta W, H2N delta H by 2 and H1N delta H by 2. So here we see, so this is nothing but this is the section A. I want to say section A is there. So from here to here, this is the section B of the path, and from here to here 1B. So then we have this one section 3. So up to here this is the section 3, and from here to here this is the section 4. Okay, so in the section 1 only one component is there. In section 2 we have 2 components are there. In section 3 for section 3 we have the 1 component, and for the section 4 again we have the 2 components which are attached to it. Okay, so by this equation we can solve, we can find the value of H as well, right? So I will rub this thing so that the things must be clear to all of you. So I'm rubbing this. Okay, so this was the equation how we are getting. So what you need to do simply now, you have to simply solve this equation and you have to put delta H tends to 0. So here when you put delta H, so you have to put the so you have to put delta H tends to 0. So here what you need to do, just put del at interface, right? At interface. So when we are talking about the at interface means delta H tends to 0. Okay, one way is this will be cancelled out. So this will be cancelled out with this will cancel out with this. But you, if in some cases if occurs that you have to find the boundary condition, so where the boundary is at the delta H tends to 0. So when you put it delta H tends to 0, so in that way this is delta W will be cancelled out here. So what equation we will get? K delta W is equal to H1T delta W minus H2T delta W. So delta W will be cancelled out. So what will left? H1T minus H2T is equal to K. K is nothing but this again the surface current. So if there is no current at the boundary, so in that case what will happen? K will be 0. So if no current at the boundary, then we have to take care about the K which is equivalent to 0. So what will the value? The H1T will be equal to H2T. So what is the statement for this? The statement for this is the tangential component of magnetic field intensity is continuous at the interface. Okay. So here we see that H1T is equal to H2T, which is not defined by the permeability. So in this case, so simple method is here to find H1T is equal to H2T. So these are the diagram which I have just explained. So here in the you can also define the value of H1 minus H2 cross A and 1 2. So A and 1 2 is simply the direction of the interface from medium 1 to medium 2, and K is the surface current density. So here we have defined this, and when you convert by using the formula B is equal to mu H, so H will be equal to B upon mu, right? So you just put it here, then B1T is upon B mu1 is equal to B2T upon mu2. So this is the tangential component of the magnetic flux density is discontinuous at the interface. I hope this point is clear. So simply what you need to do, just use the boundary conditions which we have discussed, B1n is equal to B2n, and these two equations we have to use. First equation is in the first equation which we are using here, that is here, this is the first equation, and then the second equation which we are using here, this one. So just simply convert it into that with the help of angles, then finally we will get the expression, that is tan theta 1 upon tan theta 2 is equal to mu 1 upon mu 2. So this is the law of refraction here. This is nothing but the law of refraction. So these two topics, boundary condition in electrostatic and the magnetostatic, these are very important topic. I hope you understood completely about the boundary conditions, and these are very important for the exam point of view as well. Thank you very much.